Hi, first off, I just want to thank everyone for coming to my talk. I'm Julio Rivera, and this is work that I am doing with Jesvaldo Fuentes and Emilia Martins. So the vertebrate skull can tell us a great deal of information about the different selective pressures acting on animals through evolutionary time. For example, these enlarged orbits in owl monkeys tell us that vision is probably quite important for the species. The enlarged cranium in humans tell us that our brains are much larger than our close relatives. And these large, powerful jaws in hippos tell us that biting is probably quite important for the species. However, today we're going to be focusing on Sceloporus lizards. Now, Sceloporus is a genus of lizard that's native to North America with just north of 90 species. They vary in body size from 40 to 120 millimeters snout to vent length, and they have these hallmark ventral patches that they use in interspecific communication. However, through evolutionary time, some species have lost the ventral patch. From now on, I'm going to be calling any species with a ventral patch a blue species and any species without a ventral patch a white species. So here specifically what we're asking is what are the primary axes of variation in skull shape? Does color dimorphism in the form of the ventral patches and body size play an important role in shaping the skull? And then does color dimorphism and body size interact? And so the way we approached these questions was to first CT scan 57 different species of Sceloporus lizards, and then we digitized them. And then we ran a bunch of different comparative analyses. I am not going to be talking about these today. However, I'm happy to talk to anyone afterwards about any of the analyses performed here. So we're just going to get right into the results here. So this is a PCA of a morphospace of the skull shape in Sceloporus lizards. I'm just going to walk you through this plot. Positive loadings on PC1 indicate an elongated, narrow, thin skull, while negative loadings indicate a short, wide, and more robust skull. Positive loadings on PC2 indicate a narrow and flat skull, while negative loadings indicate a wide and tall skull. I've color-coded these points so that a blue point indicates a species with a ventral patch, and a gray point indicates a species without a ventral patch. So some things I'd like to point out is that the white species are using a much more narrow morphospace compared to the blue species. Blue species also seem to be more concentrated on this left lower quadrant, which indicates a more robust tall skull, while white species seem to have a much more elongated and flat skull. Now, this is the exact same PCA that I just showed you. However, it's been color-coded by the body size category of small, medium, and large. And what we found was that, first of all, large species tend to cluster in this lower left quadrant, which indicates a much more wide, tall, and robust skull, while small species tend to cluster in the upper right quadrant, which indicates a flatter, elongated, more gracile skull. Now, this is pretty interesting because all these body size categories have been independently derived several times across the Sceloporus lineage, and we do seem to be getting a little bit of convergence in skull shape. Next, we ran a few different comparative analyses to see which factor best predicted skull shape. One of body size, and within body size, we ran one of Brownian motion and one of OU, and again, one of ventral coloration. And within this was one of BM and one of OU. And what we discovered was that an OU model for body size best explains skull shape evolution. Within the ventral coloration category, we found a similar answer with an OU of ventral coloration best explains skull shape. However, looking at all the models together, body size seems to outcompete all other models when it comes to the explanation of skull shape in Sceloporus lizards. Now looking at the body size evolution, we ran a couple more comparative analyses with 3 competing hypotheses, one of Brownian motion, one of a global optima, this OU1, and one of OU of ventral patches. And what we discovered was the OU of ventral patches best explained body size evolution. Not only that, but we found that blue species were evolving towards a larger body size optimum, while white species were evolving towards a smaller body size optimum. Okay, and just some take-home messages here. White species are using a much smaller morphospace and tend to have elongated snouts. This could be because of communication. So in our lab, we studied Sceloporus behavior, and we've discovered that white species tend to be more chemically oriented than blue species, and this elongated snout might facilitate that. Head shape seems to be driven by overall body size. However, this does seem to be an interaction with ventral coloration. But the fact that the body sizes were independently derived and converge on similar shapes could point to an integration between head shape and overall body size. We also found that blue species were evolving towards a larger optimum. This could be due to sexual selection. Blue species tend to be way more aggressive than white species, and it might be that pressure for them to grow larger compared to the white species. All right, and with that, I'd really like to thank the Martins Lab, all the undergrads that helped me digitize all the skulls, University of Washington, Friday Harbor, and Adam Summers for letting me borrow their CT scan, as well as all these museums for allowing me to borrow their collections. And with that, thank you very much.